Hello and welcome back to the lecture on applied econometrics. So we are talking about autocorrelation. In the previous lecture, we have seen something interesting where we actually plotted data and we fitted a model and we actually estimated the error term U hat, and we plotted U hat with time to see if there is any pattern existing, and we found indeed that it appears that there is a pattern, right? So it is going slowly down, slowly up, and sometimes it looks like the error is expanding with time, right? So in this kind of cases, we can basically think that perhaps there is autocorrelation, right? From the diagram, from the plot, we can make a sense that there might be autocorrelation, but to get a sort of, get the autocorrelation values in quantitative term, we need to do some tests. And we have learned a couple of tests. One was Darby-Nordsen and another was Brieusch-Godfrey. So let us actually, in this lecture, we will talk about Darby-Nordsen test if we have this kind of data and how we actually perform Darby-Nordsen test and what that means. And we again will do the test using both R and stata. Okay. So let us again sort of try to recollect the the decision rule that we use in case of Darby-Nordsen test. Okay. So we know that Darby-Nordsen test, the value actually lies between 0 to 4, right? Now if we have, let's say, if we have a number line here, I'll use a different color. If we have a number line, it starts from 0. So we remember that when the Darby-Nordsen statistic value is close to 0, we can say that there is a positive autocorrelation, right? So and that is why we said that if the Darby-Nordsen statistic value is less than DL, some lower critical value for Darby-Nordsen statistic, so we can say our decision would be positive autocorrelation. So we say the positive autocorrelation is present. If the value of Darby-Nordsen statistic is actually lower than DL. So it is close, it is basically between 0 to DL. So we can say that the value is going to be, so that we can say that there is positive autocorrelation. Then if we have, and we also said if we have the Darby-Nordsen statistic value close, let's say 2, at the value is equal to 2, we have seen that there is no autocorrelation, right? When the value is 2, when the value of rho was 0, we got Darby-Nordsen statistic value is equal to 2. So when that is the case, there is no autocorrelation, and we can, and there was a Darby-Nordsen upper du, which is the upper critical value for the Darby-Nordsen statistic, and if my calculated Darby-Nordsen statistic value lies in between these two, so then I will write that there is no positive autocorrelation. So that is my decision rule, no positive, let me write down, no positive autocorrelation. So if my DW stat computed falls in between this, there is no positive autocorrelation. And in between this, we have said that this is a gray zone and no conclusive evidence, or we can't say anything. We can't say anything conclusively. Can't say conclusively. Similarly, now we can also sort of in the same number line, we can also explain the presence of negative autocorrelation, right? So we know if the Darby-Nordsen stat value is actually close to 4, then there is a strong negative autocorrelation. And we said that we again use the du and dl here. So if we can have some critical value which is 4 minus dl, now dl is very low, dl let's say 0.5. So it is, if it is above 3.5 to 4, we say that there is negative autocorrelation. We say that negative autocorrelation. Negative autocorrelation. And if it is close to 2, So then we say that there is no negative autocorrelation, no negative autocorrelation in this zone, and in between we can't say anything conclusively, can't say conclusively. Let's say conclusively. So that is the idea. So essentially in one line we can actually summarize how we can take the decision regarding autocorrelation from the Darby-Watson statistic. And we remember we got this formula, dW is equal to 2 into 1 minus rho or 1 minus gamma, whichever we want to write. Okay. Now we got the decision rule, and now we'll first we'll use data to actually see from our previous model if we can say something about the Darby-Watson statistic. So let us go back to our data. Now we need to actually tell Stata that this data set we have is a time series data, and for that we need to write a command tset, and the time value is year, right? So the moment I say it, tset year, it will understand that it is a time series data. If I don't write, so Darby-Watson statistic will not run. So I have already written it, so now it will run, otherwise there would have been problem. Now the command is pretty simple, and the command is dwstat, that's it. All you have to write is dwstat. So the moment first I actually have to run the regression before I actually write dwstat. I have to run the regression, and the regression, so now since I already have the regression here, I have already run the regression. So my Darby-Watson test, so it will be performed on these residuals. The residuals I have got from this regression equation, the Darby-Watson test will be performed on these residuals. Okay. So I really don't have to run the regression because I have already run it, and it is stored in Stata memory. Okay. So this regression I ran in the previous lecture. So if I write down dwstat, so it actually has obtained the residual terms from the previous model, and based on that residual terms it has calculated that d statistic is equal to 1.09. Okay. And the degrees of freedom, it has 3 and 54. So 3 is the number of parameters we have to estimate, and 54 is the number of observation. All right. So we need to remember these two parameters. Note here, Stata does not say anything about du or dl, and that is a little challenge that we have, but we are going to actually resolve that. So now we see that Darby-Watson statistic is 1.09, and if I go back to this, so 1.09, so it is not 2. So let me use a different color. It is not 2. It is not 2. It is not close to 0. It is somewhere, somewhere here. So I really don't know. It might be, there might be positive autocorrelation, or there will be no autocorrelation. So there are two possibilities. Okay. So now I have to see which one is correct. Now from Stata you can't really say anything conclusively. So what you can do is, there is a Darby-Watson table available. Okay. So we'll actually search for Darby-Watson table. Darby-Watson table. So we have handy tables available in internet. So you can just open any of these. All I need is a table. So for this tutorial, this is the table. Let me actually increase the font, otherwise you won't be able to see it. So here you see, so I have these 2 degrees of freedom, k and n. Now I remember my k was 3, whereas my n was 54. So if I scroll down, I see that my values are 50, 55, 60. So I can say maybe it is close to 55. So you can approximately take the value for 55. Okay. So we'll see if that is sufficient. So for 55, for every degree of freedom, so for every value of k, they have provided du and dl. Okay. So let me actually show you. So this is dl and this is du. Okay. Now if I go down, so I'll let this first 2, and so I let this first 2 observation, 4 observation go, and I will have the du is equal to 1.284 and dl is equal to 1.505. So let me write it down. My du here in this example, my du, again let me check, 1.2 1.284, and my DL is going to be 1.505. All right. So I got these values, and my calculated value was 1.09. So my calculated value, my DW calculated was 1.09. Now what do I see from these three numbers? Now our life is easy. We have all these three numbers, and all you have to make is a decision. Now I see that DW calculated 1.09 is lower than DL, right? My DL here is 1.505, whereas my calculated value of DW is 1.09. So it is actually falling in the zone of positive autocorrelation. So my decision is going to be that my model is having positive autocorrelation, okay, from the Darwin-Watson test. Of course, you have to remember that Darwin-Watson test is actually operating with certain limitations, but we'll talk about it when we address the Bruce-Godfrey test. Now, we have seen this in Stata. Now, let me actually do the whole exercise in R. For R also, it is pretty simple. Just remember that LM test is the package you have to actually run the Darwin-Watson statistic. So here also, it is actually, you know, all you have to do is DW test, I think the command DW test, very simple, DW test, and all you have to do is to write down the name of the model here, so which is mod. So from which regression equation it will take the value? It is the regression equation which is named as mod. So if I write it here, and I will find these values here. Now look at it. So the value of DW is 1.0948, exactly the value we got it in Stata. But here, instead of, you know, getting into all these upper critical, lower critical and everything, we have a very simple p value, okay. So we know how to, what p value means. The p value is really small here. You see 6.29 into 10 to the power minus 5. So that means really low p value. So that means my alternative hypothesis is given, true autocorrelation is greater than 0, which is actually correct. So you basically reject the null, right? So essentially you say that your model has positive autocorrelation. So from both Stata as well as in R, you have seen how to run the Darwin-Watson test and how to say if the model has autocorrelation or not. So all right, so with this we sort of, you know, we conclude this lecture. We have done this hands-on on Darwin-Watson test, and in the next lecture we are going to actually do a little bit of Bruce-Godfrey test. Okay, so with this we end this lecture. Thank you.